Hello and welcome to a new video. This is for pre-calculus using the Math UC curriculum. We are on lesson 6 and boy is it about to get exciting because we're here to talk about angles of elevation and depression. As always, I have a notes page that you can download for free to follow along and not have to write as much. And because we are going to have, I don't want to give it away, but word problems, you're probably not going to want to have to write this all down. So head over to the link in the description to my website to get a free notes page, or click the thing that hopefully will show up above my head. Let's look actually at a warm-up or two first to make sure that we know what we've done up until now. Okay, we're going to do 2 warm-up problems, and these actually go along with what we did in lesson 5 in C and D on the workbook pages. And I didn't realize until after I'd already finished the video that those pages looked different and what they were asking you to do. So this is to kind of go back and say, okay, here's how we do this. This is also though going to help us with what we're doing today, so it all works out. We're going to check out this triangle. It's a right triangle, and we're going to find the value of the unknown sides and angles. We're going to round to the nearest 10th spot. So here's the thing. We know one of the angles, and we know one of the sides. Actually, we know 2 of the angles because it's a right triangle. So we know that angle, the 90-degree angle, and then we know a second angle because we know about the 55-degree angle. So since there's only 3 angles in a triangle, we can basically just subtract from 180 and get angle alpha right here. Or even better, if we realize it in time, since this is a 90-degree angle and it's pretty easy to do 180 minus 90, we really just need to do 90 minus 55, and that will give us what alpha equals. So 90 minus 55, so it takes 5 to get to 60, and from 60 to 90 is 30, so this would be 35. That means alpha is 35 degrees. Now, how about these sides? Since we only know one side, we cannot use the Pythagorean theorem, but if we find another side, then we can use the Pythagorean theorem. So in order to find either A or B, we're going to have to use the, in order to find either A or B, we have to use a trig function. So it doesn't actually matter which one we find first. I'm going to use the 55 degrees because that's the angle I was given, just in case I subtracted whenever I was getting alpha. If I use 55 degrees, it kind of takes away one of the possible places that I could get a wrong answer on one of these other letters. And then the side that I know is the adjacent side. I'm going to try to find either the opposite side or the hypotenuse. It doesn't matter which one you pick, but because I like to multiply instead of divide, I would rather do opposite and adjacent, which is tangent, because that puts the adjacent side on the bottom. In case that's not clear what I mean, let's write it out. Tangent of 55 degrees equals opposite, which is A, over adjacent, which is 14. So lesson 4, I think it was, where we solved these. I just need to times both sides by 14. Hop on my calculator, figuratively speaking, and do 14 times tan 55, making sure that I'm in degree mode. If I'd chosen to do the hypotenuse with the adjacent side, it would have worked. It would have been cosine, but since the hypotenuse is what we're missing and it's on the bottom, it would have meant I had to divide, and I like multiplying better. I don't know about you guys, but it's a personal preference. So here's our calculator, and we are going to do 14 tan 55. I had to change my calculator back to degree mode because I used it in radian mode the other day. We're going to round this to the nearest 10th, which rounds up to 20.0. So A is 20.0. Now that we know A is 20, we can use these 2 legs to find the third side with the Pythagorean theorem. We could use a trig function again. In fact, we can use any of the trig functions this time since we know 2 sides. Tangent wouldn't help us at all at this point. So we're going to do a squared plus b squared equals c squared. So on our calculator again, because these numbers are getting pretty big, we'll do 14 squared plus 20 squared, and then 596. Does that have a square root? Nope. And it didn't tell us to write this in radical form. It said to round to the nearest tenth, so I would say that this is one of those situations where you could get away with typing this in and just writing the decimal. 24.4 would be our answer here, which isn't really C. It was actually B for the hypotenuse. B equals, I already forgot what it was, 24.4. There were no units on our side lengths, so we don't need to put any units. But it is helpful because of how much work we have to box our answers so that our teacher can tell what our answers are. Now this is another warm-up, so again from lesson 5C and D. It's a little bit different, but still is using the skills kind of from that lesson a little bit. So it says find the measure of theta and alpha to the nearest hundredth of a degree and also to the nearest second. So if you remember in lesson 5, we talked about degrees, minutes, seconds. So it's saying go ahead and find it to the nearest hundredth of a degree, but also convert it to DMS. And we'll just use our calculator to do that. It'll be a really fun time. Now, from the perspective of theta, it doesn't matter which one you do. We know sides opposite, which is 7, and we know 8, which is adjacent. So we're going to use tangent for this. Tangent of theta equals 7 over 8. So to find the theta, if you remember from lesson 5, to find what theta is, we use the inverse tangent. So on our calculator, we do the tan -1, or the way that Math UC writes it in the book, I assume partially out of laziness because it's easier to write arctan than to get a -1 exponent, but I could be wrong there. These are the same thing. So our calculator has the second tangent button so that we don't have to look it up on a trig table. We can just go on there and find out what theta is. Second tan, 7 divided by 8. And it said to round to the nearest hundredth, so 41.19. That would be degrees. I was going to say we could find the other angle and then come back to it, but since I have this answer in, I should go ahead and go right away to second angle. We change it to DMS, degrees, minutes, seconds. And it says to round to the nearest second, so we'll do 41 degrees, 11 minutes, 9 seconds. Then to find our other one, we could use a trig function again, or we could just subtract from 90 because these two acute angles have to add together to make up the rest of our right triangle. So whichever way you want to do it, but I think it's easier, definitely easier to just do 90 degrees minus 41.19. Or it would be even more accurate for us to actually go back on our calculator and do 90 minus this number right here and press enter. This is 48.81 degrees. And we're going to change this, although this might actually be pretty easy to convert because we know how many minutes and seconds there should be here, that they should add up to 60. So here we go. I'm going to guess. I'm guessing this is 48 degrees, 49 minutes, because that's 60 minus 11, and 51 seconds, because 51 plus 9 is 60. Let's just check and see if that's right. Second, apps to get to the angle menu. Option 4. Yes, if we round it up to the nearest second. Oh wait, why is this 49? Interesting. Oh, you know what? There's probably a carrying thing here. If we did 9 plus 51, that would give us 1, so it would carry over to this. So that makes sense. I've just never actually really taken the time to subtract in degrees, minutes, seconds a ton. That should be a 48. So there's our answer. Okay, you may be thinking here, what's the point of us doing all this? Why do we care so much about right triangles? We've now spent, 4 weeks on this, or however long it was. And so what good does this do us? Why does this matter? Well, there's actually lots of situations where we might encounter right triangles, because we could make a right triangle any place there's a right angle at all. Like, think about the walls of your house. you probably aren't seeing triangles if you look at the walls in your house, although you might see some. But any wall should meet at a right angle down here at the bottom, which means that you could, in a lot of different ways, finish this off and draw a right triangle. Now, it may not be that you have a reason to do that in your house, but there are lots of other times where we might need to use a right triangle, or might want to use a right triangle and use trigonometry. The other thing that happens here is that sometimes we think, well, when would I ever use this? And sometimes it's not that you personally will use this on something, but it could be that something that you're doing uses it and you don't even know. For instance, trigonometry and triangles and things like that are used all the time by almost everybody, just through like the Maps app of your phone. If you've heard of the word triangulation, and they may not be right triangles all the time, they might be just whatever kind of triangles they need, but all of this stuff like is a part of our life whether we know it or not. And so I know that doesn't help if you're like, why am I having to spend all this time doing this, and why do I have to suffer through these word problems when I'm not going to do any of these things by hand? But the other part of this is that it helps us build up our problem solving skills, and it helps us to be able to think things through from start to finish and things like that. So we're going to see I'm going to do 3 examples here of some places where we can end up with right triangles helping us to find something we don't know. But there are lots of different places that we can use them. But a lot of them are visual, like out in the real world, looking at the height of something, the distance to something, the slant of something. All of those, if we could make a right triangle and know one of the things, an angle or a side length, then we could actually solve for the rest of the triangle, which is basically really helpful. Now we have some new vocabulary that we want to address. It's actually in the title of this lesson, angles of elevation and angles of depression. And once I tell you what they are, the difference between them hopefully will be easy to remember just based on what these words kind of imply to you. Elevation in general is the height of something. Depression in general, we tend to think of as being down, right? That's a very oversimplified version of the word depression, right? It's a lot more than that. But you think of, if you're depressed, you're feeling down, you're looking down. That will help us with our analogy here for our math definition. An angle of elevation is an angle that someone's telling us about where you are, from where you're at, you're looking up. That gives you your angle of elevation. Whereas the angle of depression that you might give somebody is if you are looking down. What's that angle? And so it's a comparison of the idea of looking straight forward. So if you're on the ground, for instance, for angle of elevation, if the ground is flat, you've got kind of this straight forward you can think about. And then if you're looking up at something, you've got an angle of elevation to get up to that thing. Whereas if you're on top of something like a building, then if you compare your like if you're looking straight out versus if you are looking down, and how far are you looking down, that's called the angle of depression. And what's kind of cool here is that I don't actually have triangles drawn. I can finish these off and draw some triangles, right? And I can actually draw like 2 triangles. I could draw a triangle here, or I could draw a triangle here, and then all of a sudden we can start finding sides we're missing. But also, it turns out that if you remember from geometry, our rules about parallel lines and transversals, the top and bottom here of these 2 lines are parallel, which means that whatever this angle is actually has to be the same as this one, because these are alternate interior angles. I may be really stretching your ability to remember geometry here. That's fine. But what these definitions, what's going to help us with these definitions is just they're going to help us draw an accurate picture. If you draw a problem that's talking about an angle of elevation from the perspective of somebody looking down, like an angle of depression, you're probably going to end up finding things kind of backwards. And that's not as helpful as finding them the right way. So This is the idea we've got here of what is an angle of elevation and what is an angle of depression. Example 1. So we're going to do some word problems. One of the keys to word problems in general is if it seems like there's any part of it that is something that you could draw a picture for, you should, because it's most likely going to help your understanding. Very rarely would drawing a picture hurt how you understand the problem. So let's read this. You can read it to yourself, but I'm going to read it out loud because I have to read it anyway, right? So Lee's car is parked at the base of Mount Stevenson. Lee measures the angle of elevation from the base to the summit of Mount Stevenson to be 38 degrees and also tracks his steps as he walks to the summit from the base. If he walks 8,000 feet to get to the summit, how tall is Mount Stevenson? What is the horizontal distance that Lee traveled? So we need to think about what this is talking about. Okay, so we've got our base of our mountain, and that's where our car is parked. And so as we stand by our car, we look out, and our angle of elevation, meaning we look up, this angle is 38 degrees. Now this triangle may not be very accurately drawn to scale because this person, in comparison to the mountain, is rather large. So what we need to do is we need to say, we just need to accept it because there's no way I can draw a person so small or a mountain so big. So let's see. He tracks his steps as he walks to the summit from the base. So that sounds to me like it's talking about this diagonal line. Because if it was talking about the horizontal distance, it would actually have to tell us the horizontal distance or the vertical distance or elevation or something like that. So it's actually telling us that the hypotenuse here is 8,000 feet. And then it asks us, how tall is Mount Stevenson? So that would be this over here. And what is the horizontal distance that we traveled, which would just be this other side of our triangle. So the importance of understanding the angle of elevation to mean starting down and going up is just that we shouldn't put 38 degrees here, right? That wouldn't make sense, and that would give us, we'd still get the same number, it's just reversed. So we'd say what the height was, and that would actually be the horizontal distance. We'd say what the horizontal distance is, and that'd actually be the height, and that's not great. So we want to make sure we know where to put the angle based on what they gave us. So now we're going to use trig functions to figure this out. So we've got hypotenuse, opposite, and adjacent. And we're going to find these one at a time. So if we want to find x, that's opposite and hypotenuse, which is sine. I'm thinking in my head about SOHCAHTOA, and that helps me figure out which one of these to use. So sine of 38 is x over 8,000. And then we multiply both sides by 8,000 and grab our handy dandy calculator and put it in our notebook. Wait, sorry, wrong thing. X equals 8,000 times sine of 38, and that gives us 4,925. I didn't ask you to round to something, so let's round to the nearest tenth. 4925.3. 4925.3. 4925.3. We do want to put units, and also we should say what this is. So this was the height of Mount Stevenson. So we would want to say something like Mount Stevenson is 4,925.3 feet tall. And we do that just to make it really clear to someone who's looking at this what our answer is, and also what does it mean. That's an important skill, actually, is being able to say, okay, this is the math I did, but what does that mean? Helps you a lot in statistics, especially. Horizontal distance would be this y. So instead of finding the opposite side, we're finding the adjacent side. I recommend you use the 38 and the 8,000 again instead of trying to find the other angle or trying to use the x we just found, because notice we had to round x because it was a long decimal. So this is going to help us stay away from rounding error. So we're going to do cosine. of 38 degrees equals y over 8,000. So again, times by 8,000. Remember, we have to multiply by 8,000 when the 8,000 is on the bottom. If it was on the top, we would end up dividing. So let's grab our calculator. 8,000 cosine 38. And I could have actually scrolled up and grabbed that and just changed sine to cosine, but we could argue about which way would be faster to get it. 6304.1. Whoa, I already forgot it. 6304.1. 6304.1. 6304.1 feet. And this was the horizontal distance. The horizontal distance was 6,304.1 feet. So there's our answer, and that's kind of the general way that we approach these problems. Try to draw a picture, put in all the different numbers, try to make sure that your angle's in the right spot, make sure you have enough information to find the missing sides, make sure you know what they actually want you to find here, because we only found both of them because they asked us for both. So those are kind of the steps you want to go through to make sure you get it. Example 2. A pilot is nearing a runway. She knows that the plane is 10,000 feet above the ground and that the angle of depression to the runway is 15 degrees. How far will the plane have to travel to get to the runway? Find both the horizontal distance and the actual distance traveled. So we have an airplane up in the air. You get to see my really good airplane drawing skills here. Yeah. Here's the cockpit and the pilot right here in the front. Okay, so it's saying as the pilot looks out this way and then looks down, it's saying this is 15 degrees. I think I drew it a little bit big, but that's okay. And so that means that this 10,000 feet above the ground, you can think of it as being over here, or you can think of it as being over here, right? We could actually change the orientation of this triangle and use this one instead with the 10,000, because with alternate interior angles, we know that this would be 15 degrees. Up to you, whichever way you want to draw the triangle. So it actually wants us to find both the hypotenuse and the adjacent side, because it actually specifies, because I wasn't sure how else to say it, to find the horizontal distance, so that would be either the top or the bottom of this rectangle, and then to find the actual distance, which is saying if the pilot descends right now, what is this distance that's going to be traveled? Because you know what? It's not the same exact thing, right? If we were able to travel closer to the ground with planes, technically we would travel less of a distance if we were able to still make it a straight shot or whatever, and not have to go around like buildings and things. But also there would be other problems with that, so that's why we don't do it. We're going to find the hypotenuse and the adjacent side. And like I said, it doesn't matter which one of these triangles you want to pick out to kind of use, but I'll just use the bottom one, I guess. So the horizontal distance here, to find the bottom, we would need adjacent and opposite, because this is what we know. And so that means that we're going to use tangent. So tangent of 15 degrees equals 10,000 over x. So I have to multiply both sides by x to get it off the bottom, and then I have to divide both sides by tangent of 15 to get it off of the side with x. So tan 15, x equals 10,000 divided by tangent of 15, which is 37,320.5. Sounds good. 37,320.5 feet. And I'll write a sentence at the end here and just keep on calculating for now. Now we need to find the hypotenuse, and we know the opposite side, so this is going to be so So sine of 15 equals 10,000 over h. And so we're going to do the same steps, right? We're going to times by h to get it to be over here. And then we're going to divide by sine 15. And so let's do that. Our answer here is 38,637.0 if we round to the nearest tenth. So let's see here. The x was the horizontal distance and h was the actual distance. So the plane traveled 38,637.0 feet to the runway. It traveled a horizontal distance of 37,025. So there we go. That is that example. All right, last example here. We've got a point 50 meters from the base of a billboard. The angles of elevation to the bottom and top of the billboard are 25 degrees and 32 degrees respectively. How tall is the billboard and how far is it to the top of the billboard? So you do not have to be, a super great artist in order to be able to make figures, but at the same time, it can be really helpful to make pictures that look nice. So I'm gonna attempt to do that here. Attempt being a keyword. So here's the deal. It says the angles of elevation to the bottom and top of the billboard are 25 degrees and 32 degrees respectively. So here's the edge of our billboard. Here's the ground, we're going to say, but I've got basically an angle of elevation up to the bottom of the billboard, and then I've got an angle of elevation to the top of the billboard. So I've got this situation right here. So here is our right angle, and we really have two different triangles that it's talking about, and it might help us actually to take those two triangles apart, because we have this angle is supposed to be 25 degrees. The angle up to the bigger triangle, that's supposed to be 32 degrees. So this whole thing right here is supposed to be 32. What it wants us to find is how tall is the billboard and how far is it to the top of the billboard. So I would argue that this is how tall the billboard is. And then how far is it to the top of the billboard would be this whole thing. So how do we figure that out? Right? We're going to actually need to basically find kind of three things here to end up with this height of the billboard. We can use, this is 50 meters on the bottom. So we can use 50 meters and 25 to find y. We can use 50 meters and the 32 degrees to find the whole height of this, which we'll call h. And then we can do h minus y, and that will give us what x is. So this one's a little complicated. But I think we can do it. So this is adjacent and opposite. So tangent of 25 degrees equals y over 50. So times both sides by 50 and get y equals 50 tan 25. I'm just going to leave it over here. 23.3 meters would be basically the height to the bottom of the billboard. Then we're going to do the same thing but with our bigger triangle. So this is where you may be having problems even picturing the bigger triangle because of the way it's drawn. We're saying this would be 32 degrees, this would still be 50, but we're going to get the height to the top of the billboard here. So this would be tangent again, but with 32 degrees now. So we'll do h over 50 and times by 50 on both sides. So the height to the top of the billboard, which was one of the things it asked us to find, is 31.2 meters, which means that to find x, which is how tall the billboard itself is, we need to subtract these. So 31.2 minus 0.3 is 7.9. So our billboard is 7.9. The billboard is 7.9 meters tall, and it is 31.2 meters to the top. And I feel like the wording is a little weird here. I did write this myself. So I was trying to get across the point that we wanted both, like, how big is the billboard and then how far is it off the ground, mostly just because I needed an example where we had to use this 2 triangle thing that was happening. But hopefully that makes sense. If not, ask me a question in the comments and I'll do my best to answer your question. Hey, thanks so much for watching. I hope you'll subscribe if you haven't already, like the video, leave me a comment, all that good stuff. And check out my website if you're interested for more math resources. And I'll hopefully see you again next week in the Lesson 7 video. Thanks!